Alrighty, welcome back to operating systems. Everyone's most fun class to come to while there's midterms and other courses. Yay. All right, so today pretty much just more simple stuff, more review stuff we don't actually have to know. Well, first half we'll probably want to know for the midterm. Other half is mostly for your enjoyment, and it's a good thing to know. So we can explore some dynamic priority scheduling. May also be called feedback scheduling, depending on the literature. Just another scheduling algorithm, so we're taking a rewind back. So in this algorithm, we essentially let this algorithm manage the priorities. So it scales the priorities, and the only thing you get to set is the initial priorities. So looks kind of like round robin. There's set time slices. We measure CPU usage across the time slices. And the idea behind it is we would increase the priority of processes that don't use their time slice, so they're more likely to actually get scheduled next. And we will decrease the priority of processes that use their full time slice, so they essentially give up the CPU and hopefully make it a bit more fair to the rest of the processes. Yep.
It's not like counterintuitive, like when those processes like be more important that they're using, well not important, but they require a lot of, they want to use the full time slice.
Yeah, so they can still use their full time slice, just after they're done it, they get a lower priority so that other processes can use their time slice, and then they'd get a lower priority and the one that was waiting would be higher, so eventually it would run again. It's essentially, this is just like kind of the same idea as round robin, except we're just adding priorities. So we'll see how that works in the example. So like we've been doing in Linux, the lowest number means higher priority. So for this, each process gets assigned some priority when it starts that you would be able to specify, Pn, and the algorithm works as follows. So we pick the lowest priority number, that is the process to schedule. If it yields, we just pick the next highest priority process. If there is a tie, we would just go to arrival order or something like that. If it's lower priority, if a lower priority process becomes ready, so lower number, aka higher priority, then switch to it immediately. So we have preemptions here. Then at the end of our time slice, so there'd be like an accounting time slice and then a time slice for a process, just to make things easier. So at the end of a accounting time slice, we would just record how long each process runs for in this interval. So it would be some number C to the n, where n is the process number. And in this, timer interrupts still occur. So the calculation we do is whenever we recalculate priorities, we calculate the new priority P the n as the last priority divided by 2. So it gets smaller and smaller over time because we're dividing by 2. And then we add how much time it actually used in the CPU in this time interval. And after we do that accounting, we reset every process its CPU usage back to 0. So this would be an example. We have 4 processes ready to execute in arrival order X, Y, A, B. And then we have CPU and IO bound processes. So A and B are something called CPU bound processes, which means they just want to execute on the CPU. They will use as much time as you will give them. While X and Y are IO bound processes, which means they are actually waiting for some resource or something like that, so they'll only execute for a little bit of time, and then they'll have to wait because they're interacting with a file or something like that, something that's much slower. So it doesn't need that much CPU time to make the request to the kernel, and then the kernel gets to block it until it's finally done with that request, and then it can unblock it. So in this case, we have a timer interrupt every 1 time unit. The maximum time slice for a process to execute in is 10 time units, and the priority interval, whenever we recalculate the priority for every process, is also 10. So I could make it that I recalculate the priority whenever something gets context switch. That's just a design decision you might choose. But if I have processes that are if I'm context switching between them really, really fast and they don't use their entire time slice, well, I don't want to really waste time doing accounting every time I do a context switch as well. So I might just delay the time that I pick to recalculate the priorities. So in this schedule, well, if all the processes have an initial priority of 0, then they're all tied, so they just go in arrival order. So I would schedule X first. It is an I/O bound process, so it only executes for 1 time unit, and then it's blocked for 5. So it won't be available again until time equals 6. So in this case, I've executed X, and it is now blocked, and now I get to pick between Y, A, and B. I pick Y just because it is the next soonest in arrival order. So after that, I'd schedule Y for 1 time unit, then it would block for 5, so it would be ready again after 7 time units have passed. So in this case, I just schedule process A for the rest of the time. So even though the other 2 processes are ready sometime in here, because they all have a tie for priority, you wouldn't get preempted unless you have a lower priority. So process A is the next runnable process at time 2, and it would just run until we have to recalculate the priorities. So at time 10, we recalculate the priorities and see if it's still going to run. And here is that showing that X is ready at time 6, Y is ready at time 7. And at time 10, we recalculate the priorities. So all their initial priorities were 0, and then we just add a constant number with how long it actually executed for in the last time units. So process X executed for 1 time unit, process Y executed for 1 time unit, process A executed for 8 time units, and process B executed for 0 time units. So these are all the new priorities. So because process B now has the lowest priority over every other process, we would preempt process A, and we would just schedule process B, and it would fill up the whole time slice. So it's done. Yep.
It was chosen arbitrarily.
Which one?
For A executed for 8 time units.
So the 8 in A was not arbitrary, so I'm recalculating the priorities every 10 time units. So I just took a break here whenever I hit 10 to recalculate. If A was still the lowest or tied for the lowest, it would execute for the rest of its time slice, so like 2 more units. But here, I preempt it because now process B is now the lowest priority, and I kick it out. So any questions about that? Yep.
Did you just like arbitrarily decide that like the priority of each process starts at 0?
Yep. So here at the top, it says they all have an initial priority of 0. So arbitrary, yeah, but it's there. All right, any other questions? Yep. So what it means that X and Y block for 5 time units means whenever they're done executing for their 1 time unit, they're actually waiting on some type of resource or something like that, and they can't execute anymore. So the kernel is waiting on some file to happen, something like that, and then after 5 time units, we can actually execute them again. So they'd be ready. Yep.
So just to be clear, if A came in first, it would hold the entire 10 time units.
Yep. Yeah, so if A came in first at the beginning of this arrival order, it would just hold it for 10 time units, then we would recalculate, then its new priority would be 10, and it would be the last, and then it's a tie for the rest of them. Okay, so let's see how we can do the same thing again, except set the initial priority for A and B to be 6, and X and Y can still be 0. So in that case, starts off the same. So although, whoops, should be flipped the other way, oops. Anyways, yeah, so X and Y are higher priority. It should be a lower number, but I screwed up and put it as a higher number for some reason, so it should be flipped. But anyways, same thing would still apply. X would go first because it is a higher priority process, then Y would go first, and then A would only execute for 4 time units, and then at time 6, X is ready because it gets unblocked, so it's done waiting for whatever the kernel was going to do with it, and because it has a higher priority, it would be unblocked, and since it's a higher priority than process A, it would be scheduled to run immediately, run for 1 time unit, be done. Then at time 7, Y is ready. It would execute for 1 time unit, and then it would get blocked. And then here, A would execute until A executes until we recalculate all the priorities. And then here, we would recalculate the priorities as so. So X and Y, yeah, so, oh, sorry. It says A and B have a priority of 6. Okay. I said it wrong. Sorry. All right. So process X its new priority, while its old priority was 0, divide by 2. It ran for 2 time units in the last 10 time units. So its new priority is 2. Y ran for 2 time units as well. Its old priority was 0. So its new priority is 2. Process A, its old priority was 6. So divide 2 gives you 3. Plus it ran for 6 time units. So its new priority is 9. And process B, its old priority was 6. It ran for 0 time units, so its new priority is 3. So X and Y still have a higher priority or lower number than A and B, but we see that we've now flipped and we would prefer to execute process A over B, or sorry, process B over A. So at this point, X and Y are still blocked. So X and Y would still be blocked for 2 more time units. So we would schedule process B. B would run for 2 time units, and then at that point, X is ready to execute. So X would execute again because it is a lower number or higher priority. So it executes for 1 time unit. Y would be ready, execute for 1 time unit. And then B would execute for 4 time units until X is ready again. Then X would be ready, then Y would be ready. So any questions about that? So just hops back and forth. Yep.
So we would recalculate at the end of the priority interval.
Yeah. Yeah. So you could have it recalculate at the time of every context switch, but that would probably be too costly, especially how many times we're switching here. So generally, you just recalculate at some fixed priority or some fixed interval. Yep.
What if A and B were to end and and X and Y were blocked, but A and B they finished executing?
So then our CPU would just be idle, right? Yeah. So if A and B finished and we only had X and Y and they were blocked and those were our only process, if they're blocked, we can't execute anything. Our CPU would just be idle. So we would get what? Yeah, it'd be idle for like 2/3 of the time. Yep.
In the first 10 time units, do we say X and Y have higher priority or lower because it's 6? That's confusing on the number.
Yeah, sorry. So in here, X and Y have priority of 0, and then A and B have priority of 6. So we would prefer to execute X and Y because they have a lower number. So yeah, I said it wrong before. The initial priority of X and Y are 0. Now A and B have a priority of 6, so we would prefer not to run them. But if everything's tied like before, whenever we scheduled A, it just stays until we recalculate the next priority interval. All right, any more questions about that? Fairly boring. More follow the simple algorithm. All right, so let's talk about large language models then and more fun stuff you could do. So large language models, very large, so like 30 billion parameters, and the model itself is like 20 gigs. And on some C++ project, they're like, oh, well, I have this 20 gig model, but I only need 6.4 gigs of RAM. How is this possible? And so efficient, people were discussing it on the GitHub and saying, oh, how is this ever possible? And I will teach you the trick because now you can understand it. And this is why people should take an operating systems class, because everyone thought this was impossible, but it's not. So I alluded to this last time, that we can control our process's virtual memory. So memory map, or mmap, is used to map files to a process's virtual address space. This sounds much worse than it is. I see some groans already, but this is actually a useful thing that makes your life a lot easier. So what it does is it gives you like a pointer to a virtual address, and that pointer, you can just access the file through that pointer. You don't have to use a buffer. You don't have to use anything. You don't have to worry about going to the right location in the file. You don't have to worry about literally anything. You just access it as if it was memory. No read or write system calls. You interact directly with the file system with just using memory addresses. And this is possible through the magic of virtual memory. So this mmap system call takes like 6 arguments. We can just dive into an example instead because this is fairly boring. So let's just go into a fun example. So in here, here's an example. So remember whenever we were opening a file before, well, if we wanted to read the contents of a file and then, if we wanted to read the contents of a file and shove them out over standard out, well, we had to set up a buffer. We had to open the file, got a file descriptor, did a read system call on it, and then did some stuff, and then did a write system call on it with a buffer, making sure that all the sizes were right, maybe having to retry doing the read system call over and over again, and it was a giant pain. So instead, we can make this program. So this program has the open system call, so we get a file descriptor from that. So I'm going to do a little meta thing here, and I will open this own source file with the flag read only. And then I set up this struct stat, so we haven't seen this system call yet. We won't really see it, but it's a good one to know. So this stat struct tells you information about a real file. So you can fill in that struct using an fstat system call. So you give it a file descriptor you want information about, and then the address of that struct, so it can just write the information there. Same type of deal with the rest of the system E calls we saw. -1 if there's an error, otherwise it sets error no, and you should probably check it. So here I just check that it is the success error code, and then here is my mmap. So mmap takes 6 arguments. The first argument, it looks like a lot of arguments, but most of them you don't really have to use. The first argument is an address if we were very picky about what virtual address we wanted. So you could say, I want this memory to be mapped at this specific virtual address. 99.9% of the time, you will not care, so you can just give it a null. That means I don't care where you put it. Then you have to say what the length of this is. So here in the stat struct, there is a field called st_size or _size that tells you how big that file is. So I want this virtual memory map to be as large as the file that I want it to represent. Then there is some protections. So it lets you essentially modify that PTE entry if you want different permissions. So here I have to set protection. I want to be able to read from it, and I don't set write. So if I try and write to any address that I get back from that, it'll give me an error. If I wanted to write to it, I can set a write flag if I really want. Then there's a bunch of flags with how this should behave. This is called private, so that means this memory mapping is private to your process. If you fork, the other process does not get this same mapping or anything like that, or gets an independent copy of the mapping. If this flag is shared, then both processes will map to the same physical location, and then you'll be sharing memory, which will be fun, and that's another way to communicate between processes that's really, really fast. This argument is the file descriptor, so whatever, if you want it backed by a real file, what is the file descriptor of that file? And then the last argument is just the offset. So how many bytes from the beginning of the file do I want to start this memory mapping?
So when you said if you use the share flag, is that similar to like an alternative to what we were doing with pipes?
Yeah, so that's a good question. So if I use the share flag, is that an alternative of what I'm doing with pipes? And you can think about it that way, but it's like a buffer that your processes can actually see. It's not managed by the kernel. Kernel just says, hey, both of you, you have the same memory mapping for virtual addresses, goes to the same physical memory, so you can share values. You can do whatever you want. So it doesn't have to be like a first in, first out thing like pipes. You can just do whatever you want.
Yeah, and is the stat struct, is that the same as going into the prop directory and looking at the status file? Like, is it similar?
So this stat struct is specifically for getting information about actual files. So if you read the documentation, like, so here it'll tell you exactly what everything it's for. Yeah, it gives you all probably too much information. Basically, it just gives you information about a real file, like who owns the file, like if you do ls or something like that, all that information about the file. So like here is the size, here's who owns it, here's the permission. It would all be in that stat structure. Yeah.
So is there a flag to make it so that every time you fork, it'll create a new mmap?
So whenever you fork, both processes are going to be exact copies. So if this is private and I fork, they'll both have that same virtual address, but they'll be independent of each other. So it'll be like, so private is basically like how fork behaves normally. So all your virtual memory is private to you. Okay, cool. Any other questions? Yeah, so this is fun, this is useful. So here we can check if it failed or not, and then after we have the memory mapping, we don't need the file descriptor anymore, so we can just close it. And then here, I can just, this data pointer that I got back from mmap, it is a virtual address, and I can just read it like memory. So I just read it like memory, I don't have to do a read or write system call, and how it works under the hood is the kernel knows that that virtual memory region is associated with this file. So as soon as you try to access a memory address, it would get a page fault on like the first page, and then it would read the first page of the file and then actually read that into physical memory and make sure that that virtual page maps to that physical page. So I just access it as if it was memory. So here I just access this file as if it was an array. So I just go have a for loop that iterates over every single character, and I just do a printf for that character, and then afterwards it has an associated, so like malloc has a free, munmap is essentially the free version of mmap. So if I go ahead and execute this, my key is not working, then guess what? I just get the contents of the file. And no read system call, nothing, no fuss, no muss, actually pretty awesome. So any questions about that? Yep.
So data is like a pointer to a virtual address that just stores like all the characters in the file?
So data is a virtual address where as soon as you start like accessing it, it accesses the file. So this address could be anything, but if I'm like, byte 0 here, then it would be the first byte of the file, then the third byte, and so on and so forth until the end of the file. So pretty cool, and actually this, hopefully you prefer this over read and write system calls. It's actually a lot easier, but most people won't know of this because they haven't taken this course and they don't know, they're scared of virtual memory or don't even know what it is. So since you know what virtual memory is, you can use this and it's not too bad. So why did I talk about this? So that mmap system call is lazy, so it just sets up the page table, and initially it does not read from the file. So it just creates page table entries that are invalid, that have some bookkeeping information that says, hey, whenever we try and access this virtual page, I should probably read from this file. So the kernel would store some information in the page table entry, because if the valid bit is 0, well, it just generates a page fault anyways, and the other 63 bits the kernel can use for whatever information it wants. So it can just store, a pointer or whatever that says, hey, this page should actually map to this file. So what it would do is it would just keep track on where on disk is this actual file, and then whenever you first try and access the page, you get the page fault, and then the kernel reads from that disk into memory, just so you can't even see that it's doing it, and then it would make that entry valid, and then you can just access it, no fuss, no muss. And the nice part of this is, since the kernel is lazy, well, you will only read in whatever pages of the file you actually use. So if I use the whole file, I have to read the whole file still. It's not doing anything magic. But if I only read like the first byte and the last byte, I would probably only read the first page and the last page, as long as that file is quite huge. So back to the question. So they asked, well, that file is 20 gigs. You had to read the whole thing. So how is it not taking 20 gigs of memory? How is it only when I'm using it, it only uses 6.8 gigs? So the reason this is because this whole discussion, the whole patch they made to make this super efficient and blow people's minds is, instead of opening a file and just reading 20 gigs of it, they just mmapped it. That was it. That's the whole patch. They just mmapped it. They replaced read and write system calls with just accessing memory, and that was it. And the reason it was so great is because large language models are really sparse. You don't use, for each inference, you don't actually use the entire 20 gigs of the model. You might only use a few gigs of the model or something like that. So if you just mmap it and you just use the memory directly, well, you don't have to worry about trying to be efficient or anything. You just let the kernel handle the page faults whenever they happen, and just let it load it into memory, whatever parts of the file it actually needs. So in part of this discussion, one of the experts was like, oh, there's talking about like how big the page tables need to be in order for this magic to happen, so it would have to set up the page tables. So we can actually answer that question. How much space does the kernel need for the page tables? So someone posted, you only need 40 megabytes of page tables for that 20 gig file. So they argued it was 20 times 1024 times 1024 times 1024. So this is 2 to the power of 30. So this is a gigabyte. So, and then divided by this magic number. What is this magic number? Page table size end. So we made our page tables fit on a page. It's the page size. So yeah, this is the page size, and then times 8. So times 8, why would we multiply by 8? So this is the page table entry size, so 8 bytes. So in this case, for 20 gigs of space, well, we take 20 gigs, divide it over the page size, so that is how many virtual pages I would need for 20 gigabytes, and then each of those virtual page numbers needs a page table entry, so they just multiplied it by 8, and then divided by 1024 times 1024, which is just a megabyte, and then someone clarified that, yeah, this calculation is just 20 gigs divided by the 4 kilobyte page size times 8 bytes per page table entry divided by 1 kilobyte, even though that should actually be 1 megabyte. So is this correct or not? So what do we think about this? So they just changed this and said, oh, it's 1 kilobyte, but 1024 times 1024 is actually 1 megabyte. So they just said it wrong. Yeah.
This is just a guess, but like, this is like the worst case scenario if you have to use every single page table entry. But like, according to your previous slide, that's probably not like the actual case. You're probably using only a few certain entries because you only want to access some data.
So if you do an mmap with a 20 gig file, you need a page table entry for all of it. Even if it's not going to be used, you still need a page table entry. So it might not actually like load the page and read from the file, but it still needs a page table entry. So is this the worst case or is this the best case? So, yeah, this is like the best if we only include L0, right? So this is how many entries we need in L0 page tables. How many entries do we need in L1 page tables? Probably too much to think about now. So, in fact, this is correct, but this is like best case scenario, assuming that we only used L0 page table entries and they're all, well, they would all be beside each other, but there's no multi-level page tables. So in this case, if you want to be sadistic and do like, actually, this is how much it uses, well, it's right that we need 2 to the 20 page table, or 20 times 2 to the 18 page table entries. So those are the page table entries we need across L0 page tables. So if that's how many page table entries we need, well, we know that we can only fit 2 to the 9 page table entries in each L0 page table. So we can figure out how many L0 page tables we need by just dividing it. And then we get 20 times 2 to the 9, or 10,240 full L0 page tables. So these full L0 page tables would be 40 megabytes, except we can count how many of them we need. So if we need 10,240 L0 page tables, we need that many entries across our L1 page tables. So because we need that many entries across our L1 page tables, well, each L1 page table can point to up to 512 L0 page tables. So if we just divide how many L0 entries we need, divide by how many we can fit in an L1 page table, we would get 20 full L1 page tables. So in fact, we wouldn't need just these 10,240 full L0 page tables. We would need also 20 L1 page tables, and we wouldn't count our L2 page table because we would always need an L2 page table. It would already be there for us. So actually, and this is like, you know, that whatever that meme is that nerd guy with the glasses that definitely needs to be 100% correct. So in this, actually, our best case, we would need 10,240 full page tables, which if we divide by the page size and how many entries we need, we actually need 40.07 megabytes worth of page tables, not 40. So pedantic, yes. Yeah.
Sorry, but don't we also need the same amount of L2 tables?
You only have one L2 page table.
All right.
Yeah, so in this case, this assumes that we would already have an L2 page table because our process is already running, so it would just add entries to that. Yep.
Why can the L1 page table only point to 512 pages? Why does it only have 512 entries?
So each level of page table can only point to 2 of the 9 things because we only have 9 index bits. So that means it can only point to 2 of the 9 different things, which is 512. All right, any more questions about that? That's like fun. Well, it's not that fun, but you can answer it and it should kind of make sense. Yep.
Why
So why did I divide by what? Sorry?
2 to the exponent of 20.
Oh, so the question is why did I divide by 2 to the 20 here? And I divide by 2 to the 20 here because I just wanted it in megabytes. So 2 to the 20 is just megabytes, or MIB, like the real megabytes, not the marketing fake megabytes. All right, so that's actually our best case. Did we ever need to go that far? No, but do we know multi-level page tables? Hell yeah, we do. All right, so that's pretty much it. Any other questions? Lab 3, lab whatever, yeah? So in this case, we wouldn't have the worst case because we're mapping all that virtual memory together, so all the addresses would be contiguous, so they would be beside each other in the L0 page tables. So the worst case would be like if we were like on a boundary of our L1 page tables, so we might need another one. That's pretty much our worst case. So our worst case is going to be maybe they don't exactly fill a page table. Maybe instead one has 1 entry and the other has 511 or something like that. But it's only going to affect the first and the last. So it's probably not going to be that much different. Could be, worst case would only be off by like maybe 4 page tables. No, 2, maybe 2. All right. Any other questions? Lab 3, lab anything? We can take our break. You guys are probably going to be screwed for your other midterms. So yeah, we can just end early and I will be around. So just remember, pulling for you. We're on this together.